Okay, dear colleagues, it's a pleasure for me to give this talk and a specifically special dedicated seminar, even not during the workshop. And actually, this is what I done together with my colleagues, so I should appreciate first of all Leonid Slepyan. Actually, this talk probably should be called Slepyan's method and something like this, but you would see later that it's actually mostly based on his ideas. So this also Sasha Alexander Movchan, Mike, who's here with us, and my recent PhD student and postdoc from Italy, but some other people also will be mentioned. There was participating in some of this work. So the I told this universal method, and this method really it's down to Leonid. So actually, I only want to show one more slide with my recent research interest. So this is one of them. So then I recently fallen in love with hydraulic fracturing problem. It's very rich and interesting, but the waves transform waves and factorization of matrix is much of my other interest. So I was fortunate to have some European projects, and one of them is recently running, so I appreciate it. And at the end, I will give acknowledgement to this. So the plan of the talk is here. So I first would like to give you motivation why we should do this, or why I'm doing this, maybe differently, or why it started to be done by Leonid previously, because it's not actually came from the waves problem, it came from the history from the crack problem, and then we would show a short overview what was recently done, and then we'll try to look through very simple problems and to show that we still do not know everything clearly, and we still need to do something about that. And I finish this conclusion. So this is the plan for the talk. So actually, the problem started, I would say, much earlier than that. On the next slide, I will show actually the procedure of this work. So Leonid actually delivered his first paper in 1981 called the dynamic of cracking the lattice. But the main motivation was that at that time was not really clear and understood what is the miracle behind the difference between the energy what was predicted from the theory and what was measured by the experiments. And so the idea was, if you look in a homogeneous material on the crack, you look with microscope here, and then actually you find that something has really structure inside. And if you think about the energy, what would be so if you want to solve this problem starting from the lattice structure, that clearly what is going on near the crack tip in this continuous material somewhere at the infinity in the lattice structure here. So it's typical multi-scaling problem. Then if you think about the energy you really should spend to start this propagate, and the energy what you need to apply to spend to break the first bonds here in the lattice would be not the same, and would be some coefficient in front of this. So it's my so I'm there myself to call this lattice tracking factor, but Leonid didn't do this, so this is my but the what is really important to mention, the Thomson, I don't know how to properly pronounce the name. She and Rana actually solved the problem for the two strings linked to the springs, and they actually discovered the same effect. So they discovered this tracking effect previously already, but it was not done in a general setting. So the other motivation, if you think now on that, so would be if you look at the different construction, you have a lot of them built periodically, and time to time we had disasters on them, and this disaster actually would be associated with some fracture waves, I would say. So this is famous sub-bridge pathway with Sasha with Clark to actually prove the speed of this, because this was recorded, so we can even measure the speed of this fire waves coming. And then some other phenomena also you can see in a collapse, actually on the roof, and something similar could happen if you think about interaction between the platform and LCIs and so on. But now a lot of people, really several groups working on numerous groups working on research in metamaterials. So such materials have very nice properties, and they mainly really discrete structure, and all the effects actually, if you think about it, they're associated with the dynamics effect mostly. Okay, if you think about negative Poisson ratio, it's a static effect, but most other effects are really dynamic. It's a negative masses, what John actually produced at some point. And so, but fracture is also dynamic phenomenon, it might happen here. So then what can we do to take into account not only the waves and not only the property of the material, but also what might happen to this structure? And then in sense, it will be optimization of this material, not only from one physical field, but from other. So this nice movie I borrowed from Ross McFadden when he was visiting Liverpool at one of the main occasions. And it's a famous clocking. So people actually trying to hide here some rabbits, but I suggest to hide more appropriate person than would be James Bond, I think would be much more the proper one. But from this idea actually also coming another idea that we can actually protect the Los Angeles from this very often happen earthquake, build some structure around, and then hopefully the Los Angeles would be safe after this. But the metamaterials are extremely high contrast in the sense of material, geometrical, some other properties, and the concentration of the energy is enormous. And if you have earthquake like this, what we have recently in Turkey, then I'm not so sure that any of this construction would survive itself. And then you never know whether it would be redirect the waves from the place where you want this to be redirected, or would be done something different. So I'm finishing the introduction. So I hope I persuaded you that analyzing also the fracture effects together in dynamic together with waves is also important. And this is actually the motivation, or actually the idea of methods what Leonid suggested to use in 1981. So I tried to look through this, and then everyone sees that it's nothing very specific. I mean, it's specific, but nothing unbelievable. And this really works perfectly in many cases. You would see data. So look at this completely uniform rectangle lattice. It's all the parameters here are normalized simply to not distract us to the strengths, masses, and so on. It's a simple problem. So we have link between the neighbors. There is the close neighbors, and then we have simple Newton equations here, nothing else. It's a discrete structure. Then what we have more, we have the fracture criterion here. So the first link, it's here, it may be broken. And then it's broken when this criterion would be achieved. So the elongation of this link would take some critical value. And also there is a disability condition here. So to make this, in a sense, reasonable, we will see later that it's not always happening, but that all other links would be intact on ahead of the correct tip. So only first would be broken. It's first assumption first, and then it may happen that it's not like this. So then what else? We have also initial conditions, we have boundary conditions somewhere here. We have, if it's infinite, we have radiation conditions, and then we need We are coming to dynamic process and also geometry changes in time. So we need to solve this. Okay, how to solve this analytically? Okay, how to create numerical scheme? It's another matter. So we can think about this, how to deal with all the boundary conditions and everything what would be. But think about infinite domain now. How to solve this? It's 2D discrete problem and with the moving boundaries. So the other story is that, okay, load, whatever load would be given here, we know this, but we have no idea about this, how the crack will propagate. So this is unknown. So this is one of the parameters which should be found in the solution. So the problem, because of the moving boundary, the problem is nonlinear. It's not only nonlinear because of this absolute value, because even I will take this also to remain nonlinear anyway. So it's not really the matter. So what really Leonid told us, okay, it's very natural. So let's assume that the crack propagates really steadily in a sense. So since it's not continuous material, this means that the time between the breakage would be the same. So in the same, we can recompute the velocity of this crack propagation. I think it's clear because the distances are given. Then we also assume that it would propagate straight, of course, not immediately should be, but let's assume this. And then we assume a bit more that since it's established regime, how we call it now, then the whole field would also satisfy this movement. So we would see that it would be moving in time. Actually, this is location near the crack tip would be moving in that fashion. Not actually the full, but it will see a bit later. So what if you do this? So we are coming to find the function of continuous variable eta, what originally was discrete. So we have discrete space, and now we have continuous space in one direction. So instead of the previous Newton equations, we have something like that. So the derivative is with respect to eta. So we have, I even simplify now the fracture criterion, saying, okay, we didn't have absolute values. It's simply we're applying, for example, a lot like this, and always would be absolute value would coincide with the positive side of this. But it's not that important. You can later do whatever you wish with this. But it's simply for simplicity. And then you, of course, losing your initial conditions, but you still have boundary condition and radiation conditions somehow embedded. So can we solve this problem now? Remember that now we told that previously we have discrete in both directions. Now we have final difference in horizontal direction. So we impose another link between the points which are not originally were there. So we change the problem really. And the question is, if we find finally the solution of this, would it correspond to the original one or not? So this is immediately should be underlined. So we should understand this at this very moment. But, and then to do the machinery on this, we need to do Fourier transform in direction of eta. So in horizontal direction, then the sweep method, but it depends, it's up to infinity or up to the boundary. It's simply recurrence relationship to result in another direction. If you have green functions, it would be better, so you do not need to do this second step. Then we do, using take into account the boundary conditions. You have Wiener-Hopf problem, you do factorization, you take into account behavior at infinity, so the radiation condition effectively. And then you have the result, and then you should analyze this result. And factorization, unfortunately, at this case, even if a scalar function is not that trivial, because you have an enormous amount of different points on a curve where you should do the factorization. We'll see it later in a few minutes why. So and after the finish of this all this machinery job, what is really Slepyan's method, I would say, then you would for every assumed velocity, you would have your type of boundary condition. So you should link with this, and you should find the solution with this particular type of load. So you would have a relationship between this unknown velocity you assume to be known with a real condition. This relationship is non-linear again. And then you can actually reconstruct the full field with all waves propagating in all directions. We'll see it later. So this is looking like that. Actually, I never come to the formulas, but I decided since some of us would like to see how this machinery with this green rectangle works, I simply will go through 3 slides simply showing line by line what really Leonid did. Maybe not exactly in his. So we have to solve this equation, no problem. We're using Fourier transform in either direction. Later we'll use plus minus simply to separate. That part would be analytical on the top, on the bottom, on the complex plane. So this is Heaviside function which is zero in respective domain. So taking Fourier transform, very easy. In this case, we immediately written in a bit more general form, simply taking into account causality principle to have things done properly. At infinity, that everything should be good and the solution that makes really sense. Then Leonid suggested to use these 2 functions. They are perfectly arranged for that. I still leave it like he suggested. And then you need to solve a very simple discrete equation at the full in the vertical directions. So you search first solution on the top of this, simply with inner reference. Since the coefficients are not depending on k, it's always possible. You have 2 of the solutions, so they are actually related to each other. One, I mean, reciprocal one to each other. So then we need actually something that is not growing. So it would be this one. It's shown that it's really satisfied because of the causality principle to this condition. When we reconstruct everything what is on the top, then we have symmetry just in this case, simply to understand what is going on. So it's mode 3, we have that type of load. So if something going up on the other side, would be something going down, so immediately have the solution on the other side of the plane. And the only problem remains how to find this function on the first line of this dynamic structure, of this discrete structure. So for that we should go probably okay. Okay. Sorry. Okay, I'm interested in what is going along this line. Oh, so let's assume that I have some forces here. I don't know what, but they're given because it's a correct surface. So I'm applying something on the correct surface. Those forces are actually acting. So this is something that I need to find. So one of this would be, so I'm telling this would be P plus because it's in positive part, and that would be Q minus. So Q minus, so this is known. And those should be simply. So this is the way why we have Wiener-Hopf, because we have mixed boundary conditions. So this is one type of the boundary condition. This is another type of the boundary condition. We are talking to Wiener-Hopf. So again, we're replacing in the same fashion. We're replacing the discrete problem to find difference. Applying Fourier transform. Rearranging things simply to move in one direction. But what now, if you think here, so what does it mean that these 2 parts of this structures move to each other? This means that elongation of distance would be different between the displacement of those 2 points, should be proportional to the stresses acting on this. So actually this P plus, this unknown acting, actually should be equal to 2 of displacements here, normalized value. So then we put everything inside and we have Wiener-Hopf problem. And after very simple manipulations, we finally come to the what Leonid delivers. So it's classical Wiener-Hopf with L as a kernel of this Wiener-Hopf. Q minus is a known load what you applied here, but it's also if it's applied to infinity, we have some type of delta functions or whatever specifically arranged. And finally, those 2 R and H functions simply appears here naturally as a definition of this LP. So then if you look at this problem again very closely, what you can see later that it's better probably to look at this function L as a function of 2 parameters, K itself and 0 plus ITV. Why you would see it a bit later in a few seconds. So you can analyze the property of this function. At infinity is 1, it's very good news. So if S is a real a bit greater than 0, it's never having any poles, any zeros along this real axis, K on a real axis. So they have also property of the symmetry like that. So it's a nice function, index equal to 0, you can immediately factorize it with a Cauchy integral. So what is next? So next is what I mentioned, that we split these 2, the one really variable K in 2 different pieces because of one reason. So if you try to, because we are going now to the limit with S, and this limit, you have some zeros and poles in the complex plane, everything very nice on a real resist, but you have some problems, and there's no different problems, but when a solid goes to the zeros, so they actually tend to come closer to this. And then they have to feel very strange here. So you should really later do the proper pass when you integrate this. What is written here for minus to plus infinity should be more accurate with integration over the contour gamma, and this contour gamma should be really very carefully taken. But what is interesting that if you try to find all the zeros and poles, actually they're corresponding to zeros and poles of this function are in the page. If you go to if you want to equal them to 0, it's nothing but to solve the equations KV equal to dispersion relationship. So it's something what is very nice, and you can really understand where to search for those zeros on poles, what would be the group velocities on different parts. But you also can understand what is going on here. If so, this is the line, and this angle is proportional to the velocity. So velocity goes to 0, your line will be going like that. This, and the number of poles and zeros, what you're really collecting with this, it would be higher. I mean, you would go, if V is going to 0, you're going to infinity with that. Okay, so this is Leonid in his 90s. So he's still working on his table, trying to produce some new results. And his famous trapping parameter could be simply computed with this simple formula, and this simple formula actually working perfectly okay. And the solution for this trapping lattice trapping problem should be found from this very simple. So the right-hand side simply delta function should be solved like that. But if you look here, you would see that it's really something related to scattering. You see, it's this lattice, and so this is really profile of the lattice. It's uniform lattice, but here you have deformation of this lattice in 2 directions, and you have even here something very similar to your Where is Malta? Malta is remember your ship moving here, and you have two. So these two white lines is the lines were transferring the most energy behind the ship. So very nice problem. The book is very thick, but it's like an encyclopedia, so you can look at it easily. You will find a lot of things there for starting.
What is the angle in that picture? Look like ship waves.
Yes, no, the angle its angle depends on many things. It's not the constant angle like in a ship, because the problem here is that you can make lattice anisotropic, you can have dissimilar, you can do different things. You will see it later. So this you can really change the angle. Okay, so I'm coming. So Leonid proved this mode 3, so this is simply Laplace equation, not Laplace actually, the Helmholtz in sense of this setting. And for the real full elasticity, he solved them together in 1944. And what he delivered is this is normalized crack speed, and this is energy. This one, it's a reciprocal of his what I call his parameter, but it's ratio of the energy you need to spend to break the bond, and the energy you really pump in this structure to allow this crack to propagate. And it's really not monotonic. It's monotonic only on this part for the fast moving crack. And actually this explains also theoretically observed phenomena that practice doesn't want to move very slow, so it's starting accelerate and then only coming to something and stop and start and moving more or less steadily. To model really full elasticity, you cannot do this with rectangle lattice. You should do this with triangle, but it's not the issue what I want to tell here. But what Leonid also did, he solved the static problem.
Yes, one question. Sorry,
yes. No.
Maybe you said it already. That speed is normalized.
Yes.
Normalized
to
what?
To normalize to the if it's mode 3 to the shear waves in this material, if it's elasticity to the maximum of this speeds.
But the waves are dispersive.
Yes, the waves are just
so exactly what is the shear wave speed?
Yes, yeah, okay. It's normalized to the speed of the homogenized material. Okay. If you look from the continuous
like
side.
The low frequency.
Yes. So he also moved to this velocity equal to 0. Remember, you are trying to grab all these poles and zeros. It's a really disaster. And if you try to compute somewhere here, it would be very, very difficult. You should really spend a lot of time to not miss one of those zeros, of course. Yes, please.
I apologize. This wave speed of the dispersive wave, it depends on the frequency. You said that the speed that's chosen is the zero frequency, isn't it?
No. So you have continuous material. Continuous material means that something what you borrowed from the very beginning.
I understand that, but it's something to do with the lattice, and there's some wave speed in the lattice, and it varies with the frequency. And I'm asking, what wave speed are you using?
No, it's not wave speed. It's a speed. Sorry, it's a speed It's the speed of the wave in continuous material. So I'm taking this borrowing from the continuous, from the homogenization, which is not dispersed.
Frequency limit. So now I'm asking about what happens to the high frequency phonons. Is that a bigger speed or a slower speed? If you've got phonons at a finite frequency.
We will have all the possible speeds in this discrete structure from this model. So if you come back, if you come back to the homogeneous material, you have your velocity given immediately from the equation. So this is exactly the velocity what I'm taking from. All other would come from this from the solution of this problem.
Normalize that to the highest possible wave speed. I don't know if I could be wrong.
No, I normalize by the waves from those coming not from the mass possible speed.
Actually,
Yes.
That's right. The maximum speed is the sound.
Because I think.
Yes, it's speed of sound.
When that cracks going faster than all the waves that are catching up, that's when it goes to zero.
The photons are much slower.
It's true.
That's right. So it's going to be slower than the fastest possible. Well, the fastest possible.
That's right.
And that might not necessarily be the zero frequency speed.
In this case, it is, but it may not be done.
Okay, so I'm coming back to what I wanted to tell that.
Sorry about that.
No, it's okay. So then so Leonid also solved the problem for the static problem, which could be solved without any assumptions. So you're simply using discrete Fourier transform, and apparently the same ratio, it's exactly in the same point. And this actually poses one of the mathematical problems. Since is it possible to prove the limit from one case to another case? We have two nice formulas, and then how they are actually can be delivered. The formulas actually, all this parameter, you can clearly prove, again, we did this with Leonid, that you can build this on the green functions of both problems, dynamic green functions and static green functions. So how to prove this only using this relationship between the green functions? This is still open question. Okay, I did. Then actually 10 years later, Marder and Gross picked this method and extended this for different type of structures. So we can do the lattice strip, chain structure, lattice strip in 2D. So it's with a triangle. So we found that they also made some linear stability analysis, reconstruct all the trapping effect, the stable propagating pieces, then also observe that for very high speed of the crack propagation, the branching appears, or you can assume expect branching, and they also found here something very strange, and so you see here still the linear stability portions of this curve is still possible. But what does it mean? They didn't know, so they thought that this complete story should be worked out. And they also observed, so because Leonid never reconstructed the full picture of the how displacement and everything arranged after his problems. He finished with energy analysis. But if you try, not only with energy, he actually did everything analyzing how the waves, all waves would be radiated, in which directions would be maximum of the radiation of this crack. So he did all this analysis inside. But if you look at the profile of the solution, you see that if the fracture conditions, despite that they are point near the crack tip, it might happen now that this is a crack and propagates in this direction. You may see some other points where the same fracture conditions satisfied. So what does it mean? So we do not have steady state movement. So Marder and Gross told us forbidden velocity, so we consider it would not be okay. It's not steady state fully, clearly, and there is a lot of literature in physics literature to analyze all this with things from the lattice point of view. So what I want to tell that from the applied mass and mechanics, I think point of view, this analysis was done for different type of structures, for homogeneous structures with full crack, breach crack, with interfacial cracks, and even with links built by beams, not the springs, and all this. And there are a lot of interesting phenomena comes from here. I tried to collect some results, what was done for the phase transition and for the breach crack propagation. In terms of mass, it's actually more or less the same type of problem, because how we are if we are looking on the mixed boundary conditions near and behind the crack tip, it will be more or less more or less the same, but a lot of different features are here from physical point of view. Then when the crack or fault propagates, it's also a lot of interesting effects can be found here. I mentioned about this transition event in the bridge structure, what explained the wave of this fire destruction of the bridge. Some of this I will now show when I try to move on a bit. But with the last one, I mentioned about this violation of this admissibility condition, that if you think that the criterion is broken not only near the crack tip, but somewhere in the front of the crack. But there are different fracture criteria. The fracture criteria may be not only that maximum elongation at the time, it's really the criteria of the breakage. Something happened very, very fast, extremely fast with very high amplitude. It doesn't matter that immediately would be destroyed. So there are differences called incubation time. So it's incubation time is computed the impulse of this impact. Or if it's really structure accumulated damage after 25,000 vibration may simply start doing something different. So those regimes would assume to be not really admissible from the point of view one of the fracture criteria, maybe well motivated from other fracture criteria. So we can do this. So the method was developed. So it actually shown that the kernel of the Wiener-Hopf equations actually fully correspond to the dynamic green function of the respective problem what you're analyzing. So if you think of non-uniform lattice or your crack moving not steadily, then we do the selective Fourier transform. Actually, Bazan did a lot to develop the scattering diffraction of the lattice. You're not using Fourier transform, using Z transform, but more or less in the fashion of what Leonid suggested. And some phenomenon what was discovered recently. This is actually, I would like now to point my finger in and then try to discuss with you. So with a clustering and for running as a propagation regimes, mostly. I already mentioned about the propagation with the forbidden low velocities, but we will see it a bit later. So what I really want to stop now to speak about the method itself, that if we're going from original discrete problem with really moving crack and would like to understand what would be the periodic. Actually, I forgot to mention, I should mention this later. We're speaking about established periodic regime, that the question would make, okay, when it's happened, maybe to achieve this periodic regime, maybe you should wait 3 hours and then your lattice is already finished. But actually, from the experiment, you will see it's after 2-3 breakage, crack immediately is coming to that regime. So it's very really, it's a tractable regime, really, if it exists. So you can do analysis analytically, but then you should always remember that it's not really the original problem. So you impose some additional links between the particles. So if the solution, what you assume steady state exists, you definitely recover the solution. But it may happen that you predict this steady state as something else, and then you should check what is something else. And then if you understand this is not really steady state, then you would see what is this, and it would be plus, something you can do another further analysis to do this analytically if you wish. So what is for running? It's actually, we found this in the continuous material. So you see this moving, the crack moving with the same speed, but time to time you have a small crack in the front moving with the same speed. But altogether, this speed moving much faster, this blue crack moving much faster than the red crack, the only difference was the force. And the speed is the same in a sense, if you see how it works. In the discrete structures, it's actually might compute this different structure. So you see three different type of movement. So the forerunning is the most visible here. So you have some in front again starting, and then it will be linked after this, after some time together. But difference between clustering and steady state here is not clearly visible, because the difference is the steady state is the time between each particular breakage is the same, and in the clustering it's not the same, but would be periodically repeated in a fashion. So this we call the cluster. So the cluster would be periodically moving. And then to see how it is, I put here some of the on this graph you see the average speed. So this is actually feeding wave, a push wave here. The crack propagates inside the interface. Here you see this is amplitude of the waves, and here is the average speed. So first we start with some efforts. We start moving steadily, and if you try to simulate, you would see that really you are moving on steady state like this. So then, this is predicted by the theory. This is predicted by the theory. This is predicted by the theory, as looks like a steady state regime from the theoretical point of view, from the Leonid's methodology. But if you look now, so this is okay. So we really discover what we wanted to see. But here we discover something different. So this is time breakage between the link, and you see clearly two different portions of this. It's every two. So the cluster consists of 2 points, and this is moving in front. And this would be this with that average speed. But what is, and here we have cluster with 3. And what is interesting, the nature is built like this, that it's actually, it's the average is actually moving continuously. Even this completely discrete story. And between you have some mass. You cannot understand probably this mass. I have some idea, but I do not want to discuss how you can explain this mass in between. But this mass is organized in a way that it's given this average speed always continuous way change. Then it's for the beam structure. The story is much more rich in different phenomena. So here you have the position and time. Okay, maybe I stop first to explain what is where. Okay. So here we have the position of the crack tip with time. Here we have the instantaneous speed of the crack. And here we have average speed in relation with the load. So 1 point here corresponds to the full structure here and full structure here. So this is actually behind this 1 point is the full structure, how this average speed is constructed. So let me start from the very beginning. Whether I could do this, probably yes. And the lines correspond to the steady state regime what could be predicted. So you see that clear clustering is here. 3 lines in the cluster. Then we have again something more complicated. We are crossing to the last steady state, and it's really steady state. And after this, we are coming to the maximum speed in this structure, and this will be used for running. So most of the points are coming up, so we cannot see them. Okay, and the last video, so it's Hollywood probably should finish somehow. And the last video, it's a destruction of 2 structures which are pre-stressed in different ways. So with gamma is equal to 1, the structure will be destroyed because of the pre-stress. So it's one link is shorter, the other is longer. So then you link them together, and then you cut the first link. If you look at the stick bomb, what children playing, you would see this on the internet. I have one recorded. So in this case, it's full crack with some short breach crack in the front, and here you have fully breach crack propagating because of this stress. So now we're coming, do we understand everything from what I told from the very beginning, very simple model for the lattice structure? Do we really understand everything then? So I'm coming again for the lattice, uniform lattice. We know that G0 is energy, what is necessary to break the bond. G is full energy, what we are pumping to the system. The difference, this is what John just mentioned, this would be dispersed by the waves in this lattice. And so what happens? So if we put too much energy, so the G here is in the denominator, so this line would be low enough. We have the only one intersection point, and we can reconstruct the velocity of the crack propagation here. But if you come into this point, it's not really clearly understood. So what, as I just mentioned, the Marder and Goss suggested that only that piece which is monotonically on the right-hand side would really happening. So indeed, if you are coming from that part of the curve, energy velocity curve, so we are coming here, and finally, what we to the slow speed, what can propagate in this particular structure is this one, looks like, because otherwise we are going on the left-hand side, and we have that strange problem. So the question is it really true? And probably not. So this is simply analytical solution, what coming from the methodology developed by the Leonid, but with all things done properly, with reconstruction. So here you have this diagram, energy, velocity. On the right, you have the profile of the lattice in the front before ahead of the crack tip. If it's bold, this means that the criterion is violated here. When it's only stop violated, it becomes very thin. So actually, you see, I don't know why, but if I use this device, it doesn't work. It doesn't want to continue for some reason. Moment. Yes, I'm here. So I won't really to be. Okay, sorry. So coming to the region where the red changed to the blue. And when it changed, then this admissibility condition is okay. But we're on the left-hand side of the maximum point. Okay, so the question is maybe really the minimum speed is not that, but maybe the minimum speed is this one. Huh? No. So can we really prove this? Let's see scenarios where this we have now from both sides for the same energy, we have two different velocities. So what is going on here? Okay, to do this, I need to do really simulation and to check what is going on. But to simulate lattice is a bit of hassle because I have to take too much into account. Let's see what's going in case of change. So doing the analysis with analytical solution, okay, the diagram changed a bit, but the idea of the diagram is more or less the same. We have again the red and blue color change, and then the same story happening with the admissibility conditions. So but then it will be much easier to verify the story. Okay. So to verify this, we created the experiment. So very, very long chain. Since chain is symmetric, it's from both chains are the same. We consider only half of this. So the n is a total number of oscillators. We have even more than that, but later I will explain why we are taking this. And star is position of the crack tip on this chain, and f is the position of the force on this chain. Okay. So again, everything normalized, not to consider different stories here. But now we do not know about the velocity at all. So this would be simply a result of the experiment. We are really solving the real problem. what we only want to do, we want actually to allow this force to move in actually not on the right, but even on the left. So we want to move this force. And we want to see what is going on in this case. Okay, so let's try.
Can you explain the problem again? So you've got an infinite row of these things, or a long row.
Yes.
And then you're going to do something to one of them? Or you're going
What do you mean?
one in the middle you apply a force to.
Yes.
And the other one on the left alone?
Nothing, but I have some boundary condition, of course, on the end. I will speak about the boundary condition later. So I'm taking the length of the chain is so huge, and we're computing only up to the moment when we have any reflection from any of the ends. So we are only looking at as I mentioned, we are very fast actually coming to something with a steady state, so it's good. So we can really observe story, but you would see it now. Okay, so what we are doing now, we have the solution. We have analytical solution where we compute for the different velocity in different directions. Actually, the solution what we delivered is a bit more than what Leonid did, because we really consider the moving force, but it's not important because the idea is more or less the same. So here we have the velocity of the force. So force moving on the right direction very fast, or even force moving on the left direction, but slow enough. Okay. So with the dots, it's for the different force moving with that particular velocity. And this is what we recorded, what we can catch as a steady state regime. So please observe this last points here, line points here. So they're going down. It's important. So now the question is how this diagram, or this energy velocity, relate to the velocity force. This velocity force is really monotonic now. What is good news? So we would not have any questions where it should be here or there. So this would be really answer on the question. Previously, when we are in this point on that point, it was two different points for the same energy, but there is nothing like this in that either there. So those last points they are putting on that energy diagram. So what is happening that if we move force very fast on the right, very fast speed, then all those points actually are achievable. So you simply change the force and you're moving from that point to down to here. So if you go in here, you have perfect pure steady state, because your force is moved with the same speed as a crack. But it's only possible for one particular value of the force. Then for that, a bit slower force, slow velocity of the force, you have the same story. You also have pure steady state. But even for we're still moving in the same direction like the crack tip. We are now on the left-hand side from this maximum. And the same story coming from for the steady force. And if you move the force on the left, you have but we couldn't actually come to this point numerically. So this is but we can now believe that it's possible to achieve this. But that means that we should really make an effort for what to do to come to those points. So the hypothesis is that all admissible states are possible to achieve, but then the question is how to reach those points. And what is really important to understand that if you come, for example, for this particular point to the energy velocity diagram, we can have a set of parameters, velocity of the force and the force itself, where we can come to this point. And this is important for the later discussion, actually. So this I want to pick you. So how this velocity now behaves? I'm now observing, you remember this steady, then cluster. So how this velocity really, this is velocity of the crack tip. For the smaller, when the forces become smaller and smaller, that has really created some nice laces or dynamic readings, whatever. So something like this. And in the middle, we have that steady state, what was recovered by the theory. You increase a bit, and then you have something what is really coming to steady state. So then we ask ourselves, maybe this is because of the numerical artifacts. Then I'm answering your question, Paul. So what we did, we took different type of the boundary conditions on the left, different type boundary conditions on the right. We did different lengths of the chain, and you see there is no absolute difference whatsoever. Even this is clamping or completely free boundary on the left, on the right. And if you see this, this is really artifact. This is happening because we have reflected wave coming finally from the end of this chain. So looks like everything is real. So if you look again on this construction, you see that it's clustering for the low force. Then you come to this nice building. Then you have to steady state, and then you are reaching this steady state with different frequency in a sense. Is it really so? What is going on here? So we try to understand whether we are really converging to the steady state. So we try to increase the length of the chain. So this is analytically predicted steady state. So we see when we're increasing the length of the chain and sitting long and observing what is going on, we are coming closer and closer to the steady state. So it's really converging. And also we see it's also here with amplitude, it would be smaller if you're going with a longer time and length. So, but maybe this vibration is also artifact. So then we also try to do, remember I mentioned that one point of the energy velocity diagram corresponds to the different pairs. If I take all the different pairs and compare what is going on, you see they are completely the same. So there is some miracle. We try to resolve this miracle using John and Sasha's approach with perturbation of the crack in the continuous medium. But we were not, I mean, we're still somewhere in the middle of the road. We couldn't explain this. Okay, and now the question, okay, previously what I showed you, it's only was about the velocity of the crack propagation. Now we're speaking about the full solution, how this displacement at any point, how it would be really relate to analytical solution, what is continuous, what we saw. So what is the link between these two? So this is the analytical solution versus numerical simulation. This black line is analytical solution and red lines, this is numerical simulation, this discrete points. They are moving, so simply this analytical solution is a trace of this discrete movement of this lattice structure. It's perfectly coincide with the reality, so we're very happy about this. We also do this, but previously we mentioned only about the fracture criteria on the vertical links, but horizontal links also could be brought. And if you think about this, we are coming to the same what Mother and Gross predicted from their structure. So then here you have piece of, but this piece, it's not predicted by them, so they didn't tell that it's possible. Now we know that it's possible, but anyway, you cannot go too fast because something would happen. In their case, happened this branching. In our case, what's happened that when I start doing something with this device, it stopped moving for some reason. So if you're moving here somewhere, okay, let's start. So the link which originally were horizontal, they now looks like practically vertical because we are putting them. It's a chain, so they're going in that direction. So this was originally horizontal, now they're practically vertical. But this is horizontal links, and at some point they're actually breaking the criteria in another direction. So this actually means that this crack will not propagate because the all energy when we push from that left side would not reach the crack tip. We destroy the way how this wave propagated the crack tip if you push too much energy. So what else we can say? That if the structure would be anisotropic, we discover something interesting here. So the admissibility condition also valid also on those branches as well. Also, we checked Leonid, even in his really 19th or 1870s, together with Igor Berinsky, he wrote the paper and he delivered the condition, analytical condition to check admissibility condition. And his condition actually perfectly okay for that part of the curve, but predicts something fishy here. So there is nothing here. But the condition is really perfect if you think about that part of the energy velocity diagram. And in this case, we lost even monotonicity in terms of force velocity diagram. We see here there's something happening. Something happening here, and in the simulation, the point would like to jump from that position to this position, and there is not, again, monotonic relationship, so we cannot understand this, and explain this. And even moving with a very slow speed, what would be considered, and this left-hand side from any diagrams previously considered. I don't know what's going on with this device, but you see this is perfectly okay with the simulation and analytically predicted result. If you take the dissimilar chain, but in this particular case, they're dissimilar, but the velocity of the waves along two of those would be the same. And we take the same forces from both sides, and everything is perfectly okay. It's correspond to the theoretical numerical simulation. What is happening if you take different forces? Then the full structure started moving up or down depending on where the balance condition, this balance condition would be broken. But if you take two chains of different velocities from both sides, then even you are breaking the static balance condition, it's still in a balance. Because this, along one chain, which is much faster moving waves to the crack tip, delivering energy, and there actually you see that even the red line is going not up but down. We're simply pushing this chain below, and you do not need to satisfy any balance condition. Okay, so the method is really perfect. So this is really, if someone would like to use it, it's possible to extract a lot of information. We still have some questions to understand. So as you just mentioned, we're assuming that we know the velocity, and then we find how it's come to the reality. But if you put two, it's no linear problem. If you apply different type of forces, you can have absolutely different situation. Because putting the force and putting simultaneously something like feeding wave or some scattering from some other side of this, you would have different type of destruction. Then convergence, this is pure mathematical problem to be answered. How to reach arbitrary, okay, I showed how to do this is in the chain structure, what to do in the general lattice structure, how to reach the admissible regime if you want this particular regime. What about this mini scattering or mini vibration of the crack speed? Still not. What to do with monotonic force crack speed diagram and full descriptions, clustering and running is still to follow. But it's still possible to do this, even so it's not really the only 1D, so it's a 2D. You see that we can recover everything. It's now the lattice with a thin interface in the front of okay, the crack is simply moving along the interface, which has different properties. So this is the chain of the same lattice from both sides, up and down. Then changing the speed of the crack, we see what's happening to the material in this case. You clearly see all the waves effects, what is around appears here, and the waves coming from this crack tip, and it's still, even it's dissimilar, but the velocity of the Okay, this in this case, shear waves will be the same in both, but in this case, it's answering again on Paul's question from the very beginning. You see the angles are different now from two sides. And also, if you look at the dispersion diagram, you can guess what's happening to have Stoney waves, and then we reconstruct the Stoney waves. Transmitted waves, so the crack will move. You have transmitted waves in the front of the crack. You see that the transmitted waves is not breaking the fracture criterion, and then everything could be done, and you can discover all this phenomenon. So, but when you come into the real, very complex metamaterial, what you are delivering, what would happen? It may propagate like this destruction, or may propagate along this line, or may propagate along that line, and the lines are not the same, they're all different. Or if it's a bit different type of structure like this, then there may be propagation in this direction, maybe this direction, maybe it's a bridge that propagates in this direction. So all this scenario should be analyzed, and if you want to do this, you really come into this, what I call selective Fourier transform. So you are not binded to the scalar problem, you bind to the full matrix Wiener-Hopf, and then you should do something about this matrix Wiener-Hopf. I think I come to the end simply telling you it's all for open to be considered. So how the waves, these destructive waves, propagate in all the structures. Thank you very much for your attention, and thank you for Royal Society for the Bullstone Award, to the European Union project that is still running and going on, to the Welsh government for possibility to work with an industrial company. Actually, if I have a few seconds, I could remind you that you have the invitation all to this workshop. We have 150 years of that nice cottage built on the seafront by accident, because it should be a hotel, actually very fashionable. You can imagine this. But it became a first Welsh college, and the town is like that. So if you have good luck, you have such a nice weather, you would be really enjoying. You have marine here, so then during the night time you have a lot of bars. Actually, presumably it's the biggest density of pubs in the UK, but I'm not so sure. I would not claim this. Our students claiming this, not me. And if you have your own boat for, I don't know where you can, no, okay, sail from, no. Okay, but then if you do this, you should be aware that the situation may be not that nice. So time to time it's really weird and wild, and yes, it's something. Okay, thank you very much. It's really answered. Sorry, I actually over.
Questions, or should we go to the pub? What would you prefer, Gennady?
I have a question. I always
maybe a few questions.
Yes, I always prefer questions. Yes.
John.
Thank you, Gennady. You raised a question at the end about convergence to the static. Could this be a bit problematic? Until you feel static, you've got a finite harmonic equation. You can try and approach it from a dynamic equation, say for low speed. You run out of independent functions. So is it all a bit difficult?
Yes, but
when you go from a wave problem to static, it's quite tricky.
Yes, it's true, but this is actually a restrictive problem in the sense that you are really restrict your problem. It's not the absolutely, I mean, free type of problem. So you are first of all, you are not asking about what is going on with the deformation, asking only about energy first. And second, you really prescribe all the possible conditions for the dynamics from that side. So, and since this is, yes, so I'm not telling that this is easy question. If it would be easy, probably someone already done this mathematically, but it's simply mathematical manipulation now. We have two green functions, one dynamic, one static. We have two formulas, pure coming from Fourier analysis, one from discrete Fourier analysis, another from the continuous Fourier analysis. Please prove that when the limit, when this parameter v goes to 0, we would have this. So it's not really, we are not telling that full convergence should be there. We're speaking only about that particular energy relationship should be there.
Other questions?
No, Bob.
Well, first, let's give you a round of applause.